Right, now that we've sort of finished 1.2 or 2.2, let's move on to sort of examples. So example 2.2 gives us an arbitrary function for the infinite square well with the following sort of wave function: psi of x comma 0 is equal to capital A times x multiplied by a minus x, where 0 to a is sort of the length of our well. So if we were to sort of put this into Desmos and graph it, this is the sort of wave function solution we would get. So just from this, we should be able to tell instantly that this is sort of the n equals 1 wave function, because this is just one node. And our goal is to find the time-dependent general solution psi of x comma t. So what we're going to do here is there's a few things we have to do before we can sort of move on to this. And the first thing that we should always do is we want to normalize the solution and find our normalization constant a. So that's sort of the first thing that we're going to do. That's the first thing that you're always going to do. So let's start off with that right away by enforcing that the integral from 0 to a of the magnitude of psi squared, so magnitude a squared multiplied by, and everything else is real, so we can just get rid of the magnitude sign, so x squared times, times a minus x squared dx, and we necessarily enforce that this must equal 1. So we can just sort of plug this into an integral calculator. It's a relatively trivial integral to do, but what we're going to get is that the magnitude of a squared multiplied by this integral, which turns out to be a to the 5th power divided by 30, must equal 1 necessarily due to normalization. Reverse everything, and now we have that a equals the square root of 30 over a to the power of 5. Okay, now that we have sort of the actual solution to psi of x comma 0, let's write that out. So psi of x comma 0, forgive me, I should probably add the little tail ends to this thing so that we don't confuse it with the time-independent wave function little psi. So this is going to equal the square root of 30 over a to the 5th power, and then multiplied by x times a minus x. And now our next goal is sort of to write out the general solution for psi of x comma t. And what we've learned so far is that sort of the coefficients c sub n for our wave function, given a sort of stationary state, can be described as complete. So we can write any arbitrary wave function psi of x comma t as equivalent to the summation starting at n from 1 to infinity of Cn psi, or let's just do psi n and phi n. We already know this. Also, what we know is that the phi n just becomes 1 at time t equals 0, so this is effectively identical to also psi of x comma 0 being equivalent to the summation from n equals 1 to infinity times Cn times psi n, and then phi just always cancels out to 0 at time equals 0. However, these two coefficients are apparently the exact same. So now our goal is to sort of find the coefficients Cn, and we do that as always, or as we've defined earlier, by utilizing Fourier's trick. So what we know is that this coefficient Cn is equal to the integral of the complex conjugate of our time-independent separable wave function psi sub n of x. So we're going to add a star at the top, multiplied by any arbitrary wave function f of x dx. So Cn, first off, Cn are the coefficients that go towards creating our arbitrary function f of x. So instantly, well, what we're trying to create is psi of x comma t, and sort of since psi of x comma 0 shares the exact same coefficients here, we can just say that f of x equals psi of x comma 0. And we already know what psi of x comma 0 equals. It equals this expression that we derived for the normalization constant big A earlier on. And then psi n star, psi n of x star, is just the infinite square well solution, because remember, we're dealing with sort of an infinite square well that was given to us at the start of this example. So the solutions to an infinite square well is something that we've solved over and over again. It is equal to, first off, well, there's no complex terms, so the complex conjugate psi n star is going to just equal the base solution psi n x. And this is equal to the square root of 2 over a times sine of n times pi over a multiplied by x. And from this point, we've basically finished. We just plug everything in. Cn is therefore equal to, we're going to bring the square root of 2 over a out. We're also going to bring the square root of 30 over a to the 5th out. We're going to do an integral from 0 to a of sine times n pi over a times x times a minus x dx. From this point, we can do a bit of simplification here to sort of make this a little bit easier to look at. First off, the top here just becomes 2 root 15. The bottom becomes a cubed. And we can sort of separate the solution out. First off, multiply everything by x, and then multiply everything by a minus x, sort of distribute out the solutions. And what this is going to give us is a times the integral from 0 to a times x sine of n pi over a times x dx subtracted by the integral from 0 to a of x squared sine n pi x, or n pi over a times x dx. And what we've done here is we've simply used the distributive property. This first term is going to be sine, the sine term multiplied by x multiplied by a. So I brought our a outside, and then we have x sine of n pi over a x. This second term is just a matter of taking the sine term as normal, and then we have the x going into x with a negative in front, so minus x squared times sine of this entire term. These are both sort of relatively trivial integrals to do, so we can just sort of solve them using integral calculator. If you don't know how to do this, you're supposed to use integration by parts. I recommend you learn that. But we're just going to sort of plug this into our hypothetical integral calculator, and what we're going to get is that this equals, in two cases, if n is even, then this solution is just 0, so n even. And if n is odd, then we have 8 times the square root of 15 divided by n pi cubed, given n is odd. So if we write out the full expression, which is, as we've said earlier, psi of x comma t is equal to this summation of Cn, psi n, and phi n. So let's bring this down. Okay, well, we have Cn, right? See these in different colors, just to make this a little bit nicer. Cn, oops. We already know that Cn equals sort of this big expression right here. We also know what the separable time-independent solution little psi of n is, because we sort of solved it earlier in the chapter. So we know that little psi n for an infinite square well, which is what we're describing here, is equal to square root of 2 over a times sine n pi over a times x. And we also know that the time-dependent solution, phi of n, is going to be, let's write this in blue, we also know that phi sub n is going to be an exponent e to the negative I e t all over h bar. And we know what the energy is for sort of our infinite square well. We know that E is equal to n squared pi squared h bar squared over 2ma squared. So therefore the energy must equal E to the negative I as normal. And we're going to cancel out one of the h bars. Everything else sort of comes over on its own. So that is going to give us e to the negative I times n squared times pi squared times h bar times t all over 2ma squared. And now we have all of the components that we want, so therefore we can write our arbitrary time-dependent wave function for this system as psi of x comma t is equal to, and let's sort of bring all of these constants out to the front. This is going to equal, let's see, square root of 30 divided by a, because we have root 2 and root 15 in little psi of n and c sub n. Then we have 8 over a cubed. Sorry, not a, 8 over pi cubed. Because we have the 8 expression right here, and we have the pi cubed under here. And now we're going to do our summation. And remember, since Cn is always going to be 0, if n is even, we can just say n equals 1, 3, 5, etc. to emphasize odd numbers all the way to infinity at the dot, dot, dot. And we're going to do, we have 1 over n cubed here on the Cn terms, so we're going to bring that over, 1 over n cubed. And then we have our sine term, sine of n pi over a times, I just realized, apologies, it's n pi over a x inside our sort of interval, or inside our parentheses. So let's just add that back in, n pi over a multiplied by x. And then from here, finally, I'm a little bit too lazy to write this, so I'm just going to copy paste this, our exponential. I probably should have been doing this from the beginning, apologies. But multiplied by our exponential. And this is our final answer. This is sort of the final solution to our wave function. And it's a very messy looking solution, but it is the answer. And as we will see, sort of the general solution is always going to tend to go towards these very, shall we say, complicated sort of solutions. So it's very important to sort of get comfortable writing these very long equations.